Okay, so what happened? Only 7? 6? 6. What happened to you? Okay. Okay, let's wait 1 minute probably. Okay, let's get started because this lecture is being recorded, so it's okay. Today we are going to do very interesting experiment. Okay, we are going to play with this DC motor. Okay, DC motor. Okay, so it will be very interesting, fun, and easy. Okay. We are going to still be using GPIO to control this servo motor. Okay, and also we will use a logic analyzer to monitor the signal between JetBoard and DC motor, the hardware signal. Okay, so let's get started. So servo motor is very simple. Guyun, can you please read this one for me? Read this one.
Rotation angle may be different depending on motor brand. High 1 millisecond, 0 degree. High 1.5 millisecond, 90 degree. High 2 millisecond, 180 degree.
Okay, thanks. You can check out this data sheet. There is a data sheet about that. About very cheesy. It is not explained that much. You can check out this data sheet. Servo motor, only 1 page. That's it. Very simple. Not much information. Okay. So I copy and pasted this part. Okay. So what does it say? It says rotation angle, right? So that rotation. So this wing, right? So let me show you. So I connected this wing, right? This wing. Okay. So rotation angle can be controlled depending on this high duration. Okay, what does that mean? If the duration, so that is a 20 millisecond, right? One cycle, 20 millisecond. Then duration is high is 1 millisecond. Then the wing can rotate to 0 degree like this. Okay, so, and then the high duration, high time is 1.5, 90 degree, 2 millisecond, 180 degree. So this motor wing is able to move from 0 degree to 180 degree like this, only like human arm, depending on the high time, right? And this one's supposed to be 20 millisecond. So using GPIO, we want to generate this kind of signal. Okay, this one is called PWM. What does that mean? PWM, pulse width modulation. PWM, pulse width modulation. Okay, so that pulse, this pulse width, that width, right? So you want to control this width using GPIO, right? So it is going to be easy, but you have to test a lot actually if you want to use GPIO. right? Because you have to use, wall time, your, clock, to manually measure the time. Okay. So let me show you a demo first, and we can talk more. Okay. So the connection is very simple. It has only 3 connections. It has only 3 connections. So probably should about this. It has 3 wires, right? Red is VCC. Right? Red is VCC. This one, and black is ground. So 0 volt. And you are supposed to supply voltage. Okay. Typically you have to supply 5 volt, but I did some experimentation and 3.3 volt is working okay. So our Z board, right? Our Z board is providing 3.3. So that is okay. So I connected VCC and ground. This VCC and ground to here. Okay, here. Okay. Here, VCC and ground. Okay, top. Here, VCC and ground. So check out this PowerPoint slide. So we are using which one? JB. We are using which one? This one is JB 2, right? JB 2. Okay, and then JB 2, JB 1. Okay, sorry, this one. So here the bottom output VCC and one above is ground. So I connected these two. Okay, these two. Okay, and then the remaining signal. Okay, the wire which is orange, right? Through this orange, you are supposed to provide this pulse. So I connected. Let me connect. So let me connect this one too. Let me remove this. I connect it to here. Okay. Second from the right. Second from the right. So here. Second from the right. Okay. The first one is controlling this LED. Okay, this orange wire. Okay. This orange wire is controlling LED, and second, yellow is controlling this DC motor. Okay, so then go to our hardware system. Okay, we are using what? We are using, where's the? Okay, here. Okay, here. The last time we created that project, test class, right? And open this hardware design. Okay, then there is, this one is, we have a GPIO, right? Our own GPIO that is connected to this one. This one is connected to that JB2, right? This one, right? So by programming this register, you can control that DC motor, right? So that is hardware system. Then probably let me open SDK, software development environment. Okay, this one, the Eclipse, right? Okay, last night I tested this, code. Then, okay, so this is the one we did. We created the project we created, right? So then probably we can add some, code here. So what code? I did some experimentation last night, right? So let me copy this. Copy what? This, test code, right? Very simple test code. I'm trying to generate that pulse. Okay, so motor, right? What is the address? 4120. 412. We have to change that base. Why? Because our GPIO starts from this one, I think 4121, right? GPIO 1, GPIO 1, GPIO 1. That starts from 4121. So we have to change that to 4121. And in for loop, I want to create that, that PWM pulse with modulation, PWM pulse, right? So let me copy this. That is 90 degree. Okay, look at this. So second, what is 2? 2 means what? 2 is in binary 0, 0, 0, 0, 0, 0, 1, 0, right? You want to control that, pin out, right? And then, the maintain that output during this time. So null, null loop, right? For loop, right? So that is loop count is 100,000. Then turn off that LED, turn off, right? 0, 1 is what? 0, 0, 0, 0, 0, 0, 0, 1. So you turn off, right? So second bit, right? So that is, this one is LED and this one is motor, right? Second bit. Okay. So then let it stay until this for loop, right? Then you keep doing this 20 times. So you repeatedly generating this pulse 20 times, right? So 1, 2, 20 times, right? 20 pulses. Then next, 180 degree. The only difference is loop count, right? 100,000. Then here 200,000. Okay. So if you add these two, 22 million, right? 2 million, 2 million and 100,000 if you add these two. So if you add these two count, this one and this one, 2 million and 100,000. Add these two, 201 million, right? 2 million and 100, right? Add these two, same, right? So this whole duration is the same. I'm trying to create that 20 milliseconds. I spent one whole day to cook up that code, right? 20 20 millisecond, I think, right? Millisecond, right? So you don't want to spend one whole day to cook up this, right? You try and error, right? So here, 20, 20 pulses, okay? And this one is 0 degree. So look at this, 30,000 loop count. And this one is pretty long, okay? So let me copy this, only this. And copy this to SDK. Where is SDK? So hello world, right? There is default hello world. So let me, which one I copied? I copied from, okay, hello world. So let me paste like this. Okay, copy and paste. Then probably, okay, let me add while loop. Okay, I want to do it forever. Okay, from here to until that point. That while loop. This one. I want to do this forever. While loop. Okay. Okay, then compile it. Oh, not before you compile, you have to call this function from assembly, right? So ADC, okay, here at the beginning, branch and link. What? Main hello or hello main? Main hello. Okay, main hello. Okay, about that. Compile it. Something's wrong. Problem. C code. Hello world. What is wrong?
Y문 예, 가로가 잘못해.
Okay. Here. Okay. Thanks. Compile. Okay. Okay. Let's compile. Show you this one. Turn on the board. How to fix this? Okay. So let me show you. This one is okay now. Okay, then compilation is done. Then download it to debug. Okay. So ADC, I think right session, debug. Okay, here F5. Okay, then jump to this function, branch it to this function. Then let me press F8. Okay, then show you this. Which one is F8? Nothing happens. Why? What's happening? Okay, let me turn off. Is it right? Power ground. Oh, okay. I have to change this base location. Okay, so you have to tell me, right? Okay. 4121, right? 4121, right? I have to change that base location. Okay, do it again. Okay, then download it. Okay, now F5, right? To move to that function. Then let it go. This way, this direction, right? It keep executing that code, right? So there is a 90° and 180°, then 0°. You keep executing this, right? 90, 180, right? 90, 180, 0. Okay. So again, I did this. I spent one whole day to cook up that code. Then probably you don't want to go through the same process, right? Then what do you have to do? If you can turn off. What do you want to do if you design this code first time? then how to generate that pulse, this pulse. Probably what you want to do is you want to figure out, what's going on between this board and that wire. You want to prove, you want to, figure out what's going on yellow wire, right? You want to tap into that wire, then see the waveform, right? As you run software, you run this software, you want to tap, right? You want to check out that wire status. This yellow is wire status. It is generating that right pulse or not, right? So that is why I gave you this logic analyzer, very cheesy logic analyzer, this one. So in your package, you can find this one, logic analyzer. So, actual logic analyzer is very expensive equipment, this one. Actually, it is usually comes from company called Tektronix, right? And very expensive, usually more than $1,000. I cannot give you so that equipment. So I found this very inexpensive, very cheap logic analyzer that can be used in class. Okay, that is enough in class. Okay, for that information you can. What is that? Where is that? Okay, here. You go to this. You go to this link. Okay, this one and this one. There is a short tutorial. What is the problem? Is it link? Probably I can fix this link. Okay. So there's a short tutorial and I posted installer here. Okay, let me copy. Okay. So I did that last night. Probably I forgot to post. Okay, lecture here. This one. So 7 yesterday, right? April 5th. Okay, yesterday. Okay. Okay, here, logic analyzer, right? First view. So click on this. That is installer. This one is installer. And I also posted this example C code. We just copied this one. Right? That code from you but make sure you should change this base location. Okay. So you can use this code and also installer, pulse view. Okay. Please. It freezed. It doesn't respond. Browser is not responding. I think for some reason it is very slow because I'm streaming this video, right? So computer is getting slow. Okay, so this one. Okay, here logic analyzer, installer, and example code. Okay, so using this logic analyzer, we want to do this, right? So that is a logic analyzer. Okay. A USB based logic analyzer, you should connect the logic analyzer to USB. This USB. Okay. And the other, you can prove up to, it is providing eight pins. 8, meaning you can tap 8, eight wires at the same time, okay, using that pin. Okay, so but in our class we need to tap only one wire, right? So let me create that circuit for you. Let me create a circuit. So what I'm going to do is we are going to use this breadboard to show. Okay. So we are going to use that breadboard. Let me disconnect this, pull out, then connect this one to the second port. Okay, and these 5 dots, right? These 5 dots are connected, right? So we connect that. This one, what is this? This one is a motor, right? We connect this one to here. Then what is this circuit? The yellow got connected together. So this one is coming from the board. This one is coming from the board, and that is connected to that motor input. This motor input, because these 5 dots are connected together, right? And we are going to tap one logic analyzer input to here, like this. So yellow wires are connected. These 3 yellow wires are connected. Okay, so that's the setup. Then what you have to do? What you have to do is pulse view. So I installed the pulse view. So it is scanning. So connect. So that is, if you connect USB, if you connect this logic analyzer USB, okay, then this guy pulse view software is scanning your computer to figure out, that logic analyzer. Then I think it found a logic analyzer, right? And it is very easy to use, right? You have 8 wires, right? D02, D7, 8, right? Here you have 8. So, but we will be using just one. And also very easy. Here, look at this. That is like sampling frequency. So how fast do you want to sample? It is like analog to digital converter. So it is like analog to digital converter. So we want to measure that the signal, right? And the signal is running at what? So we want to create that signal, right? It is supposed to run at 50 hertz. That is a period, right? 20 milliseconds. In other words, the frequency 50 hertz. What is the meaning of 50 hertz? You have 50 pulses that you have 50 pulses in 1 second, in every second. That is 50 hertz, meaning of 50 hertz, right? Then logic analyzer is trying to prove that signal. Then how it works is it is trying to sample. It is trying to sample that wire, the yellow wire, right? So how frequent you have to sample this? That is specified here, 20 kilohertz, or you can scroll it down, right? So you can do 48 up to 48 megahertz. That is sampling frequency. probably 48 megahertz is too fast. You don't have to use 48 megahertz, right? Then 1 mega samples. That means what? 48 megahertz sampling frequency. Then 1 million samples, right? How many? Oh, you can do 1 tera samples. Okay. So to capture 1 second worth signal, assuming that sampling frequency is 48 megahertz, then to sample 1 second, 1 second worth data. So you have to gather 48 million samples, right? Million samples. That is 1 second worth, right? Data, right? So by looking at this PWM signal, probably we don't have to have that fast frequency. Probably slow, about this 20 kilohertz. How about that? 20 kilohertz is more than enough, right? So that is 50 hertz. 50 hertz. How about that? Then, well, 50. So easy. 50 kilohertz. 1,000 times faster, right? 50 kilohertz. Then this sampling frequency is 1,000 times. Compare this number with this kilo, right? Hertz. So you have 1,000 samples. 1,000 samples within this pulse. That is enough, right? Probably to get this data. Then how many samples? 1 million, then that is translated to how many seconds? Guyun, what is that? 1 million samples. That is translated to 1 million samples, right? Then you have 50 kilohertz. Then that is what? Guyun, help me. 20 seconds, right? 20 second time. Right? 20 second time, right? So that is too much, right? Too much. So probably let's use about 1 second only. 1 second worth samples. 50K samples, right? So 50K samples running at 50. So 1 second, right? 1 second. Okay, let's do this. Then very easy. Just run it, right? Run. Try to do it. But now nothing is happening, right? Here nothing is happening. So the motor is not moving. So signal is not showing anything, right? So 50, so about 1K, 2 second samples, okay? So let me download hardware and software. And F5 and let it go, right? It is generating that first pulse forever, right? While loop. So let me just press F8. So now it is moving, right? Then come to logic analyzer and check out. Just run. Right here. See these pulses? Okay, let me turn off the noise. Okay, so look at this. You can zoom in with this. Okay, see some difference? Okay. I think this one. Okay, minus, plus. Okay, minus. Okay, here you see some difference. And let me zoom in. How to zoom in? I don't know. Okay, probably you can measure the time. Plus. Okay. You can measure the time with this probably. So 309, right? 309, 309 to 312. So 3 millisecond roughly. 3 millisecond, right? So I don't know, that is translated to what? The spec does not say 3 millisecond, but I created 3 millisecond. I think that is translated to 180 degree, right? And then how about this? Small pulse. So let me zoom in. Power plus. Three. Okay, what is that? 336 to 337, meaning 1 millisecond. Right? 1 millisecond. I don't know. That is, yeah, that is 0 degree. 0 degree. So you can prove. So using this, cheesy logic analyzer, you can prove that that contact, actual wire, right? That is how you debug actually embedded system. In embedded system design, you are creating both, right? Hardware and software, right? So you create some hardware and cook up some software, and software is running on that hardware. You are controlling hardware, right? You are controlling sensor and actuator. What if something goes wrong? You don't know, what's going on, right? Software is doing something, but you cannot see anything. Then you want to tap into actual hardware. You want to tap into, for example, you have a zinc, right? Zinc device, and some sensors are connected, right? Through this GPIO, right? Some, LED, okay? LED is connected, and that motor, right? That motor is connected, right? You are controlling something. So you want to tap, right? You want to tap into that wire and measure the waveform. In that way, you can figure out what's going on this wire while it is running software, running some software, and you can check out this wire. Right? That is typically, used in embedded system design. You go to industry, Samsung, Electronics, and LG, right? They are doing that, this debugging, right? Using that very expensive, this very expensive logic analyzer. Look at this. You have tap using this, pen-like stick. You can tap into actual, hardware contact point, hardware point, right? So you want to measure, monitor that wire. So that is a waveform you are getting. Okay. So this one is very, cheap. So I think you can purchase this at, $10 or less. Very cheap, right? And very useful for classes in school, I think. Okay, any question about this? Probably you can connect, right? You can connect the robot arm to GPIO to control that arm like this, right? Robot arm, right? Robotics, right? And drone control, I think. Gino is working on, drone, right? Probably, Gino can, use that, motor to fine control that drone. Okay, there is one kind of actuator. Right? This one kind of actuator. All right. So we can have a short class today. That is everything I prepared for today. If you don't have any question, then we can finish early. But next time, next class is presentation day, Monday, right? I ask you to cook a PowerPoint, and lucky 3 or 3 students will give a presentation. For that I wrote simple Python program, right? To select lucky people, right? Lucky student. So look at this. We are going to use that Python program. Okay, so here, what is this? Okay, project file. Recent project, not new project. It doesn't have how to go back. I don't know. Project file. Open recent. Okay, open recent. Lucky winner class. Okay, lucky winner class. Okay, open this window. Okay, I wrote this, Perl, not Perl, right? Python program, and it is taking the list of the student. Okay, AAA. So if I run this, it's annoying. What is this? If I run this, and get this. So lucky winner in this today, Mingyu, right? You are the lucky winner. Okay, run it again. Okay, Guyun next lucky guy. Run it again. Okay, Mingyu, why you are keep selected? Why? Okay, here you have a list of students, right? Mingyu 2, Guyun, 20 students. This program, yeah, Wonjun. Okay, I'm using random. I'm using random function, right? So it's fair, I think. Okay, Jungkook. Okay, so we will be using this program to select our lucky winners. Okay, and the reason why I ask you to read that data sheet is because we are going to play with that motion sensor or accelerometer, gravity sensor. Okay, you will be connecting this one to JetBoard and get some information from this board. So your position, how fast you are moving, and also it has a temperature sensor, I think. So very useful function. Okay. And also it is using special protocol. So I connected this small board to JetBoard. Through the connection, it is using that protocol called I2C protocol for data communication. Okay, for communication between JetBoard and this guy, this guy is using I2C communication protocol, and we are going to prove that signal like this using pulse of view. Okay, what's going on between these two wires, right? How they communicate each other. Right? We are going to prove that exact protocol, the I2C protocol using pulse view. Okay, there is the one. Okay, and one more thing I want to say is I posted the example project, ADC. You can download the example Vivado project from here. Okay, and then motion sensor project, I2C. You can download this example, Vivado project, hardware design and software. Everything is posted here. Okay. And when it comes to one last thing, when it comes to assignment. So here, how did you create that 1 second, 100 millisecond duration? How did you do that? Probably using for loop, right? So the one I did for this motor control, right? Then the question is, how do you determine the loop count? So you have to. How did you determine the loop count? There is a question, right? So try on error. But one thing you can think about is probably if you open this project, click on this PS. To create 100 millisecond, the pulse duration. So you are using, for loop I is equal to 0 to some, count. Okay, I plus some idle loop, right? So the question is, how do you determine this count, right? So later on, if you study timer, then this one is easy. You can set some timer to measure it, to exactly measure this 100 millisecond. But before that, how do you determine? How do you create that 100 millisecond? 100 millisecond, that pulse using software, right? This count, right? So the thing is, you have to check out first the operating clock frequency of CPU. How fast the guy is running, right? To check out this. So here the CPU is running at how fast? Our Cortex A9 is running at 666 megahertz. Okay, that means what? That means the clock, right? That means what? That 6 CPU clock, that clock. Theoretically, right? Theoretically, CPU is able to execute one instruction in each clock cycle. Okay, so for example, one addition instruction, next clock cycle, subtraction instruction, LDR instruction, STR instruction, and so on. So what if you set this count to that number, 666 million? Then probably that is going to be, what is your guesstimation? Guesstimation, 1 second? Probably not. Much longer than this. Why is that? Because we are, in this case, we are assuming, right? We are assuming CPU get instruction, CPU read instruction without any delay, But in reality, you have CPU and main memory. Here you have code and data, right? You get this code from this main memory, which is located on board outside, right? So it takes time. It takes to read this, code and some data, some, this local variable. Okay. So probably you have to, probably, divide that number by, in our FPGA system, more than 10, I think 10. So how about set this count to 6 million? So you can test, okay, 6 million. But this one is not, good, also a good count, because that, for loop will be translated into multiple instructions. Okay, and the last one will be branch. You have to go back. So depending on how many instructions CPU compiler use to translate this code for loop, right? So let's say it is five instructions. The loop count, when you execute each iteration, to execute each iteration, you have to go through 5 different instructions. Then probably divide that number by 5, right? So you get 11 million. So you get some clue, right, to determine the count and test, right? So so we have a cache. Here, but we haven't turned on that cache. So everything will be located in main memory. Get it from there, right? So the bottom line is the CPU is running at that clock frequency. So to create 1 second interval, 1 second duration, probably that is a number you want to play with first. But you want to reduce the number, okay? because of that reason, right? Main memory access time. It takes more than 10 clock cycles. Okay. In desktop computer system, it takes more than 100 clock cycles to get instruction or data. So you want to divide the number by 100 in desktop system. But FPGA based, because FPGA is running comparably slower than desktop, right? So Core i7, right? 4 gigahertz, for example, 4 gigahertz, right? Compare the number, right? Much faster, right? And FPGA system is, slower, right? So that is why, 10 probably. So you get some clue using that, using that logical reasoning. You can determine this, count. Play with the count, right? This is trial and error, right? You play with some number and measure the time with your watch. Then time is not, good. Then reduce or increase. Try and error, right? Okay, that's what you can do until we study timer, hardware component, timer, IO device. Okay. Okay, that's everything I have for today. Any question?
교수님, 그 지난번 수업에서 그 컨스트레인트 파일은 어디서 찾을 수가 있을까요?
Okay, constraint file, right? So that can be. So you don't have to right here. So you just download this. Where is the example? XADC example. This one. This project itself contains constraint. So let me show you. Take some time. Okay. Then unzip it. Okay, Vivado project. There's Vivado project. Inside here, you can find constraint, but somewhere, I think somewhere, where is that? Where do you think so? Source? Constraint here. New? LED, okay, here. LED. Okay, this one. This is the one, but you don't have to go through this, hierarchy. Just open. Pretty slow. Is it opening? Okay. Pretty slow. Okay, here example project, right? Open this block, design. Takes time. Running this Vivado, this, my local computer. This local computer is streaming out this lecture video, so even slower. So here, constraint source, constraint, right here. That includes this XDC, this one, this project. Okay. Okay. Question? Any other? Okay. Presentation. So what do you think? I don't know. Probably 15 minutes. And you don't have to use English. Just Korean is okay. So don't worry too much about language. Okay. So Korean is okay. but not much to talk, right? So here, where is that? This one. So what kind of capability it is providing, that motion sensor? That is the one. What kind of capability, right? And how to access? How to access? How to access registers? How to access register? What kind of registers it is providing? So important registers are, I think, this one, right? This one, X, Y, Z, and temperature probably, temperature, right? Those things, and probably configuration also. So every I/O device, right? Think about I/O device. Before you use I/O device, you have to set configuration. That is too obvious, right? You have to set operating condition. Then normal operate. After that, normal operation. During normal operation, this hardware is recording its status. So three different registers, configuration registers, and data register, right? Those are data register, right? Data register, configuration register, data register, then status register. So that's what you have to present. And for accessing those registers from JetBoard, we are going to use this I2C connection, that protocol to access. Very cheap, very cheap protocol, meaning you need only two wires to access those registers. That is very widely used in industry, I2C. Okay, that is why ISQ2. So probably 15 to 20 minutes would be okay. 15 to 20. Okay. Any other questions? By the way, do you have this component in package? Ultrasonic sensor. Do you have that? There's PowerPoint. Sensors. Oh, here, sensors. So what kind of sensors do you have in the package? And what kind of actuators do you have in the package? Guyun, probably. It's Mingyu, can you? So, not this IR sensor. So that is about motion sensor, accelerometer, right? And ultrasonic. Okay, do you have this one? This one? Ultrasonic? Ultrasonic sensor? That is used to measure the distance from your location to the wall. The distance, how far the location is. Do you have the sensor in the package?
있습니다.
Okay. I'm thinking about class project. So probably we can use that ultrasonic sensor. So that is used to again to measure the distance from the location to the wall. Okay, for example. So that is very widely used in robot also, right? Robot is working, or self-driving car, right? Self-driving car is measuring the distance. Okay. 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 Any other questions for today? Okay, I'll see you next time. Okay, bye.